Hello, so if you have any questions, feel free to ask. Okay, we are still waiting for some students to join. So we'll begin in a few minutes. Okay. Okay, so I think we still have some students who should be joining, but maybe we don't wait anymore. Okay, let's begin. Okay. Yeah, from today on, we will talk a little bit less theoretical stuff, less hands-on stuff. Okay, we will go to, as we discussed, we will have 2 chapters from the Foundation Data Science textbook, right, which is quite, written by theoretical computer science people. Okay, but a lot of those content are very useful, but maybe not appropriate. If you are interested, you can read them, right? For everyone, maybe it's a little bit hard. Okay. So we are taking 2 of the chapters that are super useful, okay, in practice. Right. So the first is called a singular value decomposition, SVD. I believe some of you might already heard of SVD, right? So, and the SVD, basically, you can easily find the libraries to do the SVD decomposition, right? So, for example, if you use Python, right, Python SVD, you have the linear algebra NumPy. Basically, it's linear NumPy. Okay, linear algebra library, and you can do singular value decomposition. Okay, but importantly, when do you use it? Right? What is U? What's V? Right, for example, right? And so the time when you use it, you need to understand what are the input, right, and what it will return. For example, right? So it will return. Let me see. Returns 3 items, right? You have a U matrix, you have a S, right? So diagonal singular values. You have a V, right? How to use them, right? So what, how to use them? You just call the library, but what do they mean? Okay, so you need a little bit deeper understanding, right? Otherwise, you can call the library. So, right? And when you work on a lot more complicated stuff on top of those concepts, right? So SVD is the foundation of a lot of other things, okay? And you also need to have a deeper understanding. Besides just know that there are three outputs, like U and a diagonal matrix S and another matrix V, okay? Right. So we will look at what is SVD really from every piece of the information. Right? So we will have the complete understanding of SVD of this lecture, okay? And we will look at some SVD applications in the next lecture. Okay? So that's the purpose. Right. And SVD again is in all kinds of libraries. Okay, for example, in MATLAB we also have SVD. Right. So the return value is the same. Okay. Again, it's a USV. This is the diagonal matrix. Okay. We will see what they are. Right? What is U? What's the diagonal matrix S? What's a V? Right. And these concepts are very important, so that you have confidence and you know what you are doing with SVD. Right. Then you can call these libraries. Right. And the slide has been released, I think, here. Right. You can click and download it if you want. And we will have another lecture on SVD applications. Okay, so basically this is a foundation, mathematical foundation. Be prepared that you will see a lot of linear algebra stuff. Okay, that you probably learned maybe a few years ago, right? And you totally forget. Okay, so we will recap those things, but we will discuss those things in a way that is intuitive, which means we build an intuition for you to memorize those foundational properties in linear algebra. Okay, build an intuition so you can memorize them. They are strictly derived mathematically, but probably you already did that before, but you can forget. Right? So here we will just recap those are well-established conclusions. Okay, and we build some intuition for you guys. You can memorize them and use them more intuitively. Okay. So firstly, we will review the concept linear algebra. Okay, here we have the concept of vector space. Let's take a look at what vector space means. Right. So here, vector space means you have two vectors. Okay, right, and any two vectors can generate a space. Okay, let me give you an example. Right, so on the screen you can use this vector, you can use this vector. Right, and this will generate space. That's the whole screen. Okay. For example, if you want to generate this point on the screen, that's it, right? You can sum them up. If you want to generate this point, right, you can scale them a little bit and sum them up. Okay? So basically, you can easily show that these two vectors can generate every point on the screen. Okay? So this is the screen, two-dimensional screen, is what we call. So previously we have a U, we have a W, right? These two vectors. Okay, and they can generate a subspace called a vector space, right? And that is the entire screen. Right? You just need to adjust the C and the D, right, to reach different points on the screen. Okay, so this is just one example, right? In general, your V and the W don't have to be two-dimensional, like say on our screen, right? You can have very high dimensional as long as Euclidean, it's a vector space. That's fine. Okay, U and V and W are vectors, right? And you can scale them and sum them up. You can generate a whole space, right, for any C and D values. Okay? So basically, you can consider all possible C and D values collectively. Those vectors are in the same space. Right? Of course, V and W are special cases where you put 1, 0, another 1, then you get this. Right? And we can easily prove some interesting properties. The first property is that if you have two subspaces, right, S and T, okay, and their intersection is still a subspace. Okay, so all these things can be mathematically strictly proved. Okay, but we will not prove that in this class, right? Because this is not a math class. Okay, it will waste too much time. For the basic stuff, we will just quickly review. But let's build some intuition for you, right? So when you prove it, how do you do that? For example, you have two vectors, V and W. Okay, they are in the intersection of S and T, right? So you can show that this thing is in S, right? Because they are in S. Okay, right? And you can also show this thing is also in T, right? Because each of them is in T, right? So of course, in this intersection space, if you have any two vectors, okay, and this thing is also in their intersection. It's both in S and in T. Okay, so you can prove things like that mathematically if you have a very rigid math course. But here, just keep in mind, vector space is if you have a bunch of vectors and you generate them by a linear combination, which means a weighted sum, okay, with different weights, right? All kinds of weights. They will generate a whole space. It doesn't have to be two-dimensional, okay? And if you have two such spaces, their intersection is another subspace, okay, which means it's closed, right? So if you have two and any in this space, any two vectors, then you take a linear combination of them. It's still in this space, right? And we will be particularly interested in three kind of space, okay, subspace relevant to matrix. Okay, the first is called row space. The second is called column space. Okay, the third is called null space. And again, if you have any question during the process, feel free to stop me. Okay. So firstly, let's look at the column space. What is a column space? These, as we described, these things are defined for a matrix, something like this, right? And the column space, apparently, we are thinking those V, W previous vectors as columns, right? So basically, you know, this is a vector, this is a vector, this is a vector, this is a vector. Okay? Right. And we know that we can write a linear equation, right, like this. Right? If you have AX, and then you have another column, which is X1, X2, right, something like this. Blah, 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 equal to B. Right? B is another column. Okay? Let's say B1. Then it means this row times X1, X2. Right? Weighting by the first row can be B1. Okay? Weighting by the second row can be B2. Okay? So this is a linear equation. So, and here, as we discussed, we will regard this matrix A as a row of column vectors. Okay? This is column vectors, C1, C2, Cn. Okay? And we have a row of those column vectors. Right. And next, let's look at how can we decompose it. Right. So you think about it. So this is using block matrix concept, which means, for example, if you think this A now becomes C1, right, C2, okay, all the way to Cn. Okay, and you are timing X in the meanwhile, right? And X we know is X1, right, all the way to Xn. Okay. And this looks like what? This looks like an inner product, right? Right. C1, X1, C2, X2, etc. Okay. Then you sum them up, right? But in order to do this kind of block matrix computation, you need to make sure their dimensions matches, right? Okay. So let's take a look at whether their dimensions matches. Right. So first, what is C1? C1, you can see this is m rows, n by 1. Okay. One column. Right. And we look at X. X is 1 by 1. Okay. Yeah, they match. Right. So because when you want to do multiplication, these two. Okay? If they match, then you can just expand it like this. Right. So this is some common technique, and to help you see things more clearly. Right. So what does this mean here? So that means that for the system to have a solution, right? This is a linear system. Okay. So for this linear equation system to have a solution, B must be in the span of the column vectors, right? So here, because let's just look at this side, right? So we already tell you how to go from here to here, and just look at this side. That means B is in a space that is generated by C1, C2, Cn, right? A linear combination of them, okay? X are the scalars, okay? It's the column vector, X1, X2. Okay? So that means, if you have C1, C2, C3, right? So we have C1, C2, C3, right? And they will generate a whole 3D space. B must be inside this 3D space, right? Again, it's not so intuitive because human cannot imagine beyond three dimensions. But again, those vectors, how many vectors? This can go up to n dimension in the worst case, right? Because they're independent component of n. Right? So here we can see that B must be in a span, or we say a span generated by these vectors, okay, which is the subspace generated by C1, C2, all the way to Cn. If your B is outside them, then you are in trouble because, for example, again, let's use two-dimensional to describe. Okay, let's say you have C1, right, is something like this. Okay, and for C2, you may have something like this. Okay, but they are all on this screen. Okay, then all you can get is, using a combination, right? Using, X1, C1, X2, C2. Yeah, so please stay muted if you don't have a question. Okay, thank you. And so it will generate the entire screen, right? Okay, but what if your B has some component coming out of the screen? Okay, it's difficult to plot, right? So just to think about there's some small component. You think about it's facing you. Okay, then no matter how whatever value you give to x1, x2, right, you will not find a solution that can give you to B. Okay, because there's some small component coming towards you, and these two vectors C1 and C2 are totally in the screen. Okay, so that's the intuition here. But B must be in the space generated by the C1, C2, C1. Right, we call it a span. This is the terminology. There's also concept of row space, and the row space is also intuitive. Right, this is one row, right? R1, R2, R3. Okay, so we have so many rows. Yeah, something like this. And now, if you write something like this, right? So let's say A, okay, you write it like R1, R2, Rn, right? So this is the same thing, okay? Because R1 is the first row, okay? AX is what? So you times this thing with X, right? So can you write it out like that? Of course you can write it out like that, but you don't have inner product because this looks like a column, right? Another reason you don't have to write it out, because if you look at the dimension here, what's the dimension of this person, this vector? It's one row times n columns, right? Because it's n. Okay. And in the meanwhile, if you look at the x vector, right? It's the n item, x1 to xn. So it's n by 1, right? So of course these two matrices, okay? So the output is one value, right? So which is here, right? So put simply, this is really the first row times the first x column gives you this, inner product between the first row and this. Okay. Then the second value is this second row. So yeah, so in this case we use the entire x, unlike the previous case, right? So these are different ways to represent this AX. Okay. The previous one we need to write out like x1, x2 components of x, but here we will just use the entire x. And so another important concept, I believe everyone heard of it, right? So whether you still remember it, not, right? So we will give you intuition. Okay, we will not prove those things. Right? Take these conclusions, and they are well proved. Okay. Firstly, rank A. What is rank A? Rank A is a dimension of the vector spanned by, A's rows and columns. So basically, we are saying, hey, so for example, for this space, right? How many dimensions do you have? Okay. So you think about it. If you have just one column vector, another column vector, C1, C2 are along the same direction, you only have one dimensional space, right? If you have another, you have some component orthogonal to it, right? So you are not totally on the same. You have the two-dimensional space because it's the whole screen. Okay. If you have some other component coming out of this screen, right? Then you have three-dimensional space. Okay, right? So this dimension, how many dimensions you can, right? And we can show that at most you can have n dimensions, right? Whenever you add a new vector, right? You think about the previous space, you at most have some component orthogonal space. The other are inside that space, right? This orthogonal dimension of your vector will decide the new dimension. Okay? Whenever you add a vector, each time you can only at most add one more dimension, okay, to the whole space of the span, right? So this is the intuition here. And there's also like a concept of rank, right? So rank is what we just said, right? So this space, this span, right? So how many dimensions is a space? Okay, so that's a span. This is the rank. Okay, and for the row space, you can also use a weighted sum of those things, right? It will also give you a row space. Okay, that's irrelevant to this, right? Because it's a weighted sum of R1, R2, R3. Okay, so rank is equal to the dimension of the vector that span by its columns or by its rows. Right? But you may ask why you can either use column and rows, because there's a proof showing that row rank and column rank are the same. Okay? Basically, if you have the number listed like this, okay, like this A, and you take all the columns, And you think about the span of that. So the dimension of that space is going to be the same as if you take this row and then compute a weighted sum, right? The span of this row space. Okay? Their dimensions is going to be the same. Okay, you can prove that. So this is called the row rank or column. Okay, and there's a concept for the matrix, right? So if the matrix is full rank, it means you know. So here's the meaning. Okay, so again, n and m can be different, right? But at least along one dimensions, all of them add some new component, right? So these are called linearly independent, right? So if you let's say this vector equal to the previous vector's sum, then this adds no more information. There's no new vector, right? So if you every row or every column adds some new information, okay, right? And then you are full rank. Okay, so full rank is equal to m or n. Okay, but we will take the minimum, right? So because for the other dimension, you must have some redundancy, okay, depending on the shape. Right? So because you have, if you look at the linear equation, you have less equations, right, than the unknown variables. So you have multiple solutions for that. Okay, so then basically your dimension is actually not so high. You can have lower dimension. Okay, because there's more freedom. That means you wasted you added some unnecessary dimension. Okay, so basically full rank means you at least one along one side, right? Whether it's a n or m, okay, right? You are full. Okay, all these vectors are linearly independent. Okay, none of them can be a combination, linear combination of the other vector. Okay, so this is called a matrix full rank, right? And we will see a few concepts relevant to full rank. Okay, so again, we will just get the conclusion and give you intuition. And the mathematical proof should be in your linear algebra textbook. Okay? And the full rank is very important because that's relevant to like whether it's degenerate matrix, right? Whether the determinant is zero, right? So so in depending on the textbook, some say this is determinant, right? Others say, hey, this is determinant. Okay. If you look at the matrix of this shape, determines these two times minus these two times. Okay, if you have any impression of those linear algebra stuff before. And the third vector space is called the null space. Right? The previous two space is pretty straightforward because we generate the whole span, right? And it's of course a linear space. Okay, the null space is we need some proof. Okay, right? So you think about instead of b, right? We put a 0 here. Right? Ax equal to 0, right? And if this is the case, then we need to show that if we have two vectors, right? One is x1, and we have another vector which is x2, right? And the linear combination of them are they still in this space? Okay, that's the question. Right? If that's the case, like x1 plus x2 still satisfy this requirement, then that's right. Like we can say this is a valid vector space, okay, subspace. Otherwise, we cannot say that, right? Let me, okay, so the answer is actually true, right? So if you look at you look at here the vector space, right? If you think about ax and x1, x2, right? Whether this summation vector is still hold, right? If the summation of xa is equal to ax1 plus x2, each one is 0 from this equation, right? So the whole is still there. Okay, right? Another question is if it's linearly scaled, right? So whether it's this, right? Because this is a constant, right? It's a scalar, you can move it up. Okay? Because this part is 0. Okay, so the whole thing is 0. Right? And because of this reason, we can show that any linear combination of them, right? So for example, you can first scale x1 into another x3, right? By some c, okay? And then you can scale x2 by some into x4, right? Each of them, according to this formula, is 0, right? And then you can sum them up, right? This becomes a linear combination, okay? So you just need to show summation and the scaling is the same than any linear combination is the same, okay? So here, that now we have those x1, x2, those kind of even x1 plus x2, right? They are inside some space, okay, subspace, right? And this is a valid subspace, vector space, okay? But how many dimensions is this space, right? So this dimension is called a nullity. Okay, the dimension of the null space. Okay, all those x that satisfy this requirement, these vectors constitute a space, and the dimension of that space is called a nullity. Okay. And we have the rank nullity theorem. It's telling you something like this, right? So your rank of the matrix plus the nullity is equal to n. Okay, if you come back, you know that n is what? N is the number of columns. Okay, so what does that mean? Right, that means, because keep in mind this x is a long distance associated with columns, right? So it really depends on how many equations you have, how many unknown variables x1, x2 you have, right? If I think in earlier maybe elementary school or high school or junior high school, you probably learn these things, right? So if your rank of the matrix is not full, which means your equations are not equal to the number of unknowns, right? For example, your equations is less less than, right? You have many x1, x2, x3 that can satisfy these equations. Okay, then actually you have you lose some dimensions, right? You don't, even though you have 10 columns, but your dimension actually only is maybe 7. Okay, where are those other 3 dimensions? They are in the null space. Okay, the nullity is 3. Okay, their sum will be 10. Okay, this n is the number of columns in A matrix. I hope this will be clear. So again, so this proves like a rank nullity theorem is out of the scope of this course. Okay, but just remember the conclusion. If you put this 0 and those x, they constitute a space. It's a valid vector space, and the dimensionality is really the number of columns of matrix A minus the rank of A. Right? The rank of A is how many information the rows and the columns of A has. Okay, and there are certain ones that are in the null space. Okay? Of course, if you have a 4-rank matrix, right? Then the nullity is 0. Okay, and so the null space of A is this, we call it the orthogonal complement to the row space. Okay, so what does that mean? That means, if, let me give you some example. Okay, maybe this is your A matrix has three columns. Okay, this A matrix has 3 columns. But these 3 columns are all in this string. Okay, are all on this string. Then actually, you have a null. Your x in the null space is coming out of the screen. Okay, there's another component coming out. This is called orthogonal complement, which means every vector inside the if you look at every vector inside this row space. Okay, this again it have to be row space, not column space. Okay, because we know the rank is also the column rank, row rank is the same. Okay? But in order to prove this, you have to look at the row space. This theorem is for row space, R1, R2, R3. Okay, and here you have this. Right? So if you look at those those different rows, you generate a new vector here. Okay, and it's going to be orthogonal to any. Let's say your column space is not just the one dimension. Okay, you have another one that can be generated by those kind of vectors. Okay, and you can easily. It may not be that easy, okay, but you can prove any such 2 vectors. I think I should not use any 2 such vectors have a perpendicular degree, right? And they are orthogonal, which means, hey, if you are on these 2 dimensions, I'm on these other 2 dimensions. They are orthogonal. Okay, so this is called orthogonal complement. Again, I'm just building the intuition. Okay, yeah. If you have any questions, just let me know. Okay, then let's move on. Yeah, so previously we talked about the vector space, right? So next, let's look at the concept of eigenvalues and the eigenvectors, okay? So here, we call, if you remember, right, so AX equal to B is the vector, okay? So you can look at this linear system as something like this, right? You put a vector inside, right, a number of variables, it will give you a vector output variable, right, like B, okay? Right. But this times a matrix. So this linear system, right? If you time A, this is a linear equation, right? It gives the output of B. So when we talk about eigenvalues and vectors, we actually require these 2 are in the same space. Okay. So what does that mean? You think about A is an n by n matrix. Okay. I think we should reverse it. Right? So this is our previous method. Okay. We have n rows and n columns. Okay. And X is a column vector. Right. So n columns and one row. Okay. Right. So we have A and we have X. What's the size of B? Who can tell me? Anyone can tell me? I think this is pretty easy, right? Right. So this matrix times this matrix. This will give you an n by one, okay? N by one size column. So B is of this size, X is of this size, right? So how can you make sure these two column vectors, right? So many rows, one column. Okay? These two column vectors are in the same space. This can only happen if your n is equal to n, right? Okay, so they have the same number of dimensions as they are in the same space. If your dimension number is different, then they are indifferent. This also means that your m is n, so A is square matrix. Okay, this is the requirement. And now that what does this mean here? Okay, this means originally you have a vector right in the same space. After applying, it will become another vector B, right? This is X, this is B. But then that's not good. Okay, that's not good. We want to find a particular, so there are so many different X you can handle with A, right? There are all kind of vectors you can handle. But there's particular vectors. When you time with A, right, this X times with A, it will give you another vector, B, along the same direction. Okay? Okay, it's just a scaling. This is the scaling. Okay? Scaling A by different size. Okay? This is ln X. Of course, it can be negative. You can go this way. But you are on the same line, okay? Same direction. Okay? If that happens, those X's are special. Describing this matrix. Okay? Those X are called eigenvectors. Right? And the associated scaling factor, lambda, are called eigenvalues. Okay? Right. So this has to be square. And we can show that such these eigenvectors, X, right, all eigenvectors associated with a given eigenvalue form a subspace. Okay? So we are talking about, again, each eigenvalue decides a subspace. Okay? Right? And you can have multiple, maybe x1, x2, all satisfy this. Right? But if that happens, you can show that there are linear combination, right? It still satisfies this. Okay? Still satisfies this. This is not difficult to see, right? You time them out, right? A, C, X, right? And you can move C out. So you have C, A, X, okay? This is C, A, X. And you know AX is ln X, so this becomes ln X, okay? So you can easily prove this. So now we know that for the same eigenvalue, the associated second vectors are also in subspace. Okay? And the next is that how can we compute, right? So how can we satisfy this requirement, right? Or we say how can we compute these lambdas, right? Or X, right? So so apparently, if you get x0, this will trivially fold, okay? But that's not meaningful, right? You want to find non-zero eigenvectors, right? And still satisfy this. These vectors matter a lot, okay? 0 is not meaningful, right? So I mean, it's not, it doesn't have a direction, okay? It's just stay in the origin. So yeah, we will do some change, right? So you know this equation equal to ax minus ln x, right? Ln x equal to 0. Okay, we just shifted the right-hand side to the left-hand side. Okay, but by doing this, if you want to factorize x out, right? So you want to have something like x and something here, okay, minus something. You cannot do that, right? Because A is a matrix, ln is a value, right? So you can add a identity matrix, right? Because I times x is x itself, right? And then you can have A minus lambda I, okay, which is basically a matrix where the diagonal is lambda, other side 0, right? So this gives you something like this, okay, right? And we can show that determinant is basically saying how large, right? How large the vector is, the matrix is, right? In terms of the dimensions. Right? And so we want to compute the, because x is 0 is fine, but we are considering non-zero eigenvectors, right? And if that is the case, if you take the determinant on both sides, okay? So previously we have this thing equal to 0, right? Then you can take determinant on both sides, okay? And if you take determinant on both, let me maybe derive a little bit. Previously we have a minus lambda I, okay, that's right. And when we have this, we basically equal to 0, right? And then we can, on both sides, we can take determinant. And this is scalar, determinant is still 0, right? And on the right-hand side, we take determinant, but this thing, we are not considering 0, okay? So this cannot be 0. So we have to make the determinant this, right? And when we do this, actually, you can show that this is an n-dimensional, because A is n by n-dimensional equation, okay? And so this is called a characteristic equation. Right? Let's think about a simple, A is A, B, C, D, right? Okay, and we are minus lambda, right? So this is lambda. Okay, the other two are 0. Okay, and then you want to compute, these are matrix values, okay? Well, and then you want to determine, right? So what will happen is this is finally after minus, it's A minus lambda, okay? B, right? C, and D minus lambda. Okay? And when you compute a determinant, I think you should know this, right? So this is this thing and this thing first, right? This becomes a lambda square or something, minus BC, okay? But this will give you a square, right? But this is because A is 2 by 2, right? In general, if you have n dimensional, this will be an n-dimensional, order n equation of lambda. Okay? You know that this can have at most, n roots, right? So n roots, okay? N values, the n lambdas that can be considered. Some may not be real number in the complex field, maybe. Okay. So yeah, here's the derivation, right? So if you want this thing to be equal to 0, right? But x is not a 0 vector, right? X is a 0 vector is trivial, okay? And then you have to have this thing, Oh yeah, so here's another derivation, okay? This may be more accessible because you may not be familiar with determinant, right? So you just time A minus lambda I, okay? Inverse on both sides. Okay, this times anything is 0. Okay? And this cancels, then let me see. Yeah, so how to say this? If you have inverse that exists, then you can time on both sides. Okay, left, left. Then you can always show that x is 0, right? Because you can cancel inverse. Okay, so for this non-trivial case to happen, so this thing should not exist. Okay, so again, we can show that for a square matrix, if you don't have inverse, okay, you are not 4 rank. Okay, if you cannot, this cannot happen, then your rank is not n. Okay, rank is not n. And if your rank is not n, that means your determinant, okay, is 0. Right? Only 4 rank matrices has determinant. As long as you're not 4 rank, your determinant is going to be 0. Okay, and so these things are all occurring. The 3 conclusions. Right? So whether you have an invert matrix, remember A is squared. The second is whether your determinant is not 0. Right? The third is whether your rank is 4 rank. Right? So these 3 are occurring. Right? So again, the detailed proof of those things are in the textbook of linear algebra. So just remember the conclusion. Okay. Now we show that if you want a non-trivial x, this thing has to be not exist, which means you cannot be taking inversion. Okay, that means your determinant is 0. Okay, because you are not 4 rank matrix. And there's also another interesting conclusion that for a symmetric matrix, which means Aij equal to Aj. Okay, and if they are symmetric and their entries are real, right? Real means you don't have any entries like A. There's a complex number, right? So A plus B, okay, and its conjugate number is A minus B. You don't have those I there, right? So it's a real number. Every entry in the matrix is real, okay? And this A is symmetric, then all eigenvalues are real, okay? You can show this, right? All these eigenvalues, which means you can find n such roots, okay, to make this real. But again, there's no guarantee your matrix is symmetric, right? And if that happens, maybe some of the lambda values does not exist if you just consider real space, right? If you go to the complex space, you will find some complex roots. Okay? And this is where in linear algebra, people sometimes talk about complex matrices, right? You can see, yeah, even if all your entries are real, okay, because your matrix is not symmetric, right? You can generate something that is complex already, right? Like this then. Okay? So there's not a clear boundary between real number and and the complex, except for some special cases. Let's say you always work with symmetrical, which actually is the case in a lot of real applications. Like if you do PCA, right? So this A is correlation matrix, right? How the I and the J and the I are correlated. They are always symmetric. There's another concept called invertible, right? So no, not in, called a similar, right? Similar matrix. Okay. And if you look at the complex domain, they call it unitarily equivalent, right? But now we are only considering the real domain. Okay, all matrices are real numbers. Okay, and so what does it mean by A and B are similar? Right. That means if you exist a matrix P, that you can take the inverse of it, which means this P inverse exists. And then you can do something like A equal to P inverse times B times P. Okay. So A and B are similar. What does that mean? Firstly, they mean that A equal to this, but this is not intuitive to you. Okay. So if you wanted some intuition, the answer is that A and B have the same eigenvalues. Okay. Eigenvalues is a special feature for the matrix. Right? Each matrix has a bunch of eigenvalues computed from here, which is a Euclidean matrix. Okay. Right. And so really, the eigenvalues decide the feature of the matrix, right? How the matrix property of the matrix. Okay. So they are special. And if A and B have the same set of features, right, then they are similar. Okay. So how can we see that, right? So why they have the same eigenvalues, right? If we satisfy, so now we are going from here to here. Okay. So from here to here, same eigenvalues. Right? How do we know, right? How can we go from here to here? Okay. Yeah, let's do some simple derivation. Okay. Now we want to, you know that according to the eigenvector eigenvalue concept, right? You have ax equal to lambda x. X is the a's eigenvalue. Lambda is eigenvector. Lambda is a's eigenvalue. What can you derive, right? So we know that A is equal to what? Right? A is equal to P minus PP inverse BP. And so you have this, right? And then you can do what? You can left multiply P on both sides, right? You can times the P here, that's then the concept. Okay? These two concepts. You can times P here. Okay? Then you will get something like this. Lambda can move different because it's stable. And now if you look at Px together, what do you find? Keep in mind, P is a square matrix, X is a column. The output is still a square matrix. Like this, you consider Px equal to B. Okay, so we have this B times the vector equal to lambda times the vector. So what? So lambda is an eigenvector B. Okay, so here we show that if lambda is eigenvector A, lambda is also an eigenvector. Okay, and you can easily also prove the reverse, right? Because if you move this here, that's this is B, this is P minus, right? But you may see, hey, this P minus after it, right? P is first. But you can define Q, right? Q minus A Q equal to B. Okay, where Q is P's unit, right? Then they are in the same form. Okay? All right. So you can go both directions. Okay. So put simply, so the reason we are defining something like, if you have this P inverse B P, right? Then they are similar. So reason is because they have same eigenvalues, right? And if you want to know why, you can put it here and derive. You will see. Okay. And there's also a concept of, so this is a generic case, right? So we will have some concept in the more general case, more special case, okay? The diagonalizable, we'll see what it means. Okay. Yeah, let's, because this is quite math intensive, I think we can take a 10-minute break, okay? And then I will come back and we will continue at 5:55. Okay. Thank you. Let's take a small break. Okay, I think we are coming back. Okay, so let me. Only one minute left. We will begin. So, by the way, taking this time, do you have any questions regarding those previous slides we covered? Because it's quite intensive, right? So, but we are just talking about the intuition for you guys to understand. Okay, and we are not proving anything, but they are well proved. Okay.
So not yet, but I'm sure I will have some questions eventually once I look at it again.
Got it. So you can understand this stuff, right?
Yeah.
Okay, good. Yeah.
It's been a long time, but
exactly.
I got it, basics.
Exactly. Yeah. So again, for no matter what the math, you need to get the intuition, because that's when you get the intuition, you know how to use it, right? So if you just see the proof and that's correct, and then pass, right? Maybe after 2 years you forget everything. Okay. So just like if you now do derivative, you will never derive the take the limit, right? You just know that derivative formula is like this. Okay. So we are just building some intuition, and then we move on to the SVD. Right. Okay, so let's continue. I think that's the time. All right, so yeah, where are we dropping? Yeah, we go to the next page. Okay. Yeah. Previously we talked about any matrix A and a B, right? So and the P is anything. Okay. Now we are just basically talking about P should be diagonal. Okay. So firstly, give you guys some intuition. P, we are talking about something that can be diagonal. Okay. Oh, I think let me see. No, we are talking about B is diagonal. So A is not diagonal, but we can convert it to B, and B can be some diagonal matrix. Okay. Here B can be anything as long as you have a B and make it similar. Okay. So what if A is similar to a diagonal matrix B, right? So in that case, we will use I think we are using notation D. Okay, D is a shorthand notation for diagonal. Okay, instead of B anymore. Right? So A is diagonalizable means that it has another diagonal matrix, and they have the same eigenvector, right? Because eigenmatrix, as we said, eigenvalues, they have the same eigenvalues, okay, according to the previous. As we said, eigenvalues are the features of that matrix, okay? And if your A has the same features as another matrix that's a diagonal, then you are diagonalizable, okay? And A is similar to a diagonal matrix, right? And these are equivalent, right? Because this is definition of diagonal. But more important is this, right? So if that happens, A has n linearly independent eigenvectors, okay? Because previously we talked about this, right? So these eigenvectors, okay? So they may not be linearly independent, right? So previously, because they may be in the same space, okay? But if A is diagonal, okay, then A has n linearly independent eigenvectors. Okay, n is the number of columns and rows of that. A is square matrix. Okay. This is pretty pretty strong, right? So it's because A only has n dimensions, okay, and it has n linearly independent eigenvectors. Those eigenvectors really contains the entire A's information. Right? Okay, let's take a look at how to prove it. Right? So why? So we are proving something like this. Right? So we are saying A is diagonal, which is equal to we have a D matrix which we can be similar, right? Okay, and then we want to show this, right? We want to show something in red. Okay, we want to show that A has n linearly independent eigenvectors. Okay, and we want them to be linear n of. Okay, how can we do that? So here, let's just write things up, right? So here, let's change another color. Okay. Let's use this. Why it's not working? So let's use this equation, okay? And you can time p on both sides, right? This will cancel. Just time p on the left hand side. So you will have something like AP, okay, equal to PD, right? You just it's the same thing. Just take the opposite of left hand and the right hand side. Okay. But what is AP anyway? Right. So what is AP? AP, if you write a P like a column, right? P is P1 all the way to Pn. Okay. And so this is really, if you look at the block matrix notation, A is maybe n by n, P is column vector n by 1, right? So you can time them together, right? So it becomes this. Right? This is the resulting, the first column in the result of this product. Okay, this is the first column in the second, in the result in the second column. Okay, so something like this. So this is a block notation of AP, right? And we also have PD, and we just started that they are equal, right? Because because of this relationship, these two are equal, okay? Because they are similar. A is similar to this diagonal. What is PD anyway? Right. So PD is something, something like this. Okay. If you cannot see intuitively, let me tell you what. Right. So if you have a diagonal matrix, okay, and you time them on the right-hand side, then you are scaling your columns. Okay. Right. If you time on the left-hand side, you are scaling your rows. This is the conclusion. Okay. But if you are not familiar with those intuitive operations, then let me derive this for you. Okay. So you can write P out, as we said. P is P1, blah, 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 Pn. Okay. Right. And we also have something called a diagonal matrix, right? So diagonal matrix is something like lambda 1 all the way to lambda n. Okay. Something. And how do we see this thing is this thing, right? So this is the question. So you think about it, right? So what are you missing when you want to do block matrix computation? Right? So here is it's something like inner product, right? This is a row, right? So so this is like how to say it? Yeah, we cannot do the inner product by the way. So right multiplication is equivalent to scaling this column by lambda 1 and scaling the second p by lambda 2. Okay. The time on the right hand side, you are scaling the rows. Right? Okay. But let's don't go to these magic solutions that if you are familiar with linear algebra, you know, right? But let's see how we can derive them. Okay. So the solution is really, let me see how to say that. Okay. Let me see. So this, let me see. You can write it out. This P is n by 1, okay? So you want to 1 by something, right? So the only way you can do this is you make this a row, this a row, this a row. Then you will get 1 by n, okay? Right, this is 1 by n. Okay? So here we can think about something like this. We can define an EI, right? So this is like if you have 0, 0, 0 everywhere, but you have 1 at i's position, okay? And then you have 0, 0 everywhere. Right? This is EI. So if you look at this first row, it will be what? It will be lambda E1, okay? Lambda E1. Lambda 1 E1, okay? The last row will be lambda n E1, okay? Right. Then lambda 2 E2, right? Because E2 is the second position, it's the other 0, and then you scale them by lambda 2. Okay? So finally, what you get is this matrix, right? Lambda 1 E1, lambda n E1, where each row vector is of size n by 1. Okay? 1 by n. Okay? And we know that this is what? This is n by 1, right? And then you can, let me see how to say this. Okay? You can, this is row, this is column, right? So you can time them together, I think, right? So you can have the, if you think about the notation in an inner product manner, right? So this is P1 times lambda 1, okay? And plus P2, blah, 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 okay? Plus Pn, lambda n, right? And so the lambda is a scalar, you can move it out. Right? So put simply, you have a bunch of this thing. You have lambda I and pi ei, okay? And keep in mind, ei is a row vector, right? It's a row vector, and pi is a column vector, right? So what does that mean? Okay, when you have a column vector times a row vector, it gives you a matrix. Okay, this is called an outer product, right? Okay, and now let's look at what does for example, let me use a notation. What does P1 E1 mean? Right, so basically it's the first term here. Right? If it's 1, what does that mean? Right? And you just think about it. if this is the P, this is E, right? And you know, only the first location is on, okay, right? And then this P, you know, the first row times the first column, okay, right? Because this is 1, so your value is staying here. The second row times the first column, your value is staying here, right? So this column is exactly this column, right? But if you look at the first row times the second column, it's 0, right? Everything else is 0. So if your you know, PIEI, P1, E1 is the first column, okay? And the others are 0, right? If you look at P2, E2, what is that? Right? So for example, here you have your P2 is a column vector, right? And you have E2, E2 others are 0, only the second value, okay? So what will be P2, E2? P2, E2 will be a matrix where every other things are 0, but the second column is P2, okay? Just look at right? The first row times the first column, this is 0. And times the second is this is the value P. Okay? And similarly, if you look at the value, it will be the value P. Right? So basically, we are saying that, you know, okay. So if you times these together, or you times these together, that will give you a matrix where, you know, this is the Pn's column, this is P1's column. Okay. Right. And you are scaling. Right. And if you sum them together, because, you know, if you are at column 1, all the others column 1, 0, right? So it's like a scaling the columns. Okay. So that's why we get the conclusion. But anyway, just keep in mind, if you right multiply a diagonal matrix, you are scaling the column matrix. Okay. If you left multiply a diagonal matrix, you are scaling the rows. Right? That's probably the easiest way to see those. Okay. Otherwise, you have to work with the block matrix notations. Now, as we said, according to this formula, these two are equal, right? So that means, because they are equal, right? This is the first column, okay? Because these two matrices are equal, so their first column must be equal. The second column also must be equal. The nth column must be equal, okay? So basically, we are saying, you know, all these are equal, right? So here we are saying that, you know, another important conclusion is this, right? You say that P is forward, P can take inverse, okay? So keep in mind, if your matrix can take inverse, which means your P is full rank, which means you have really n dimensions, right? Linear independent PIs, because the columns are all independent, right? And then you got invertible. All these are, you know, all these are equivalent, okay? And you know, so this basically proves our theorem, because, you know, according to diagonalizable, which is this, right? We showed that, you know, those PIs are linearly independent, right? So they are linear. Otherwise, it will not be full rank. You cannot take it in. Okay? Right? And in the meanwhile, these independent are eigenvectors. Right? Why is eigenvector? Because, you know, this equal to this, and P1 is an eigenvector. Right? And this equal to this, P2 is eigenvector. Right? So this gives the conclusion that all of those P, right, those column vectors, right, are the eigenvectors. Right? So if you look back to this conclusion, it does not just tell you that, you know, A is diagonalizable, right? A can be equivalent to a, similar to a D, right? It also tells you that if you do this, right, this P matrix, these columns are its eigenvectors, right? And they are linear independent. Okay? These n linear independent eigenvectors are those columns of P, such a P. Okay? So this is what this is telling you. And so usually we will go a step further, go to even more special case, right? So which is P is orthogonal. Okay? And P orthogonal means, you know, P is invertible, and in the meanwhile, your inverted matrix, okay, is the same as your transpose. Right? Okay? So this is called orthogonal. So I hope you are familiar with this. So orthogonal matrix is basically you have a P and you have another P, right? So they are the same P, by the way. Okay? But you take the transpose, right? If you take the transpose, originally your P, maybe this is row 1, row 2, row 3, row 4. Okay? You take transpose, it becomes column 1, column 2, column 3. And because you wanted this also to function as a P inverse, right? Which means if you time them together, you want to make it identity matrix, right? Which means it's 1, 1, 1. Okay? Others are 0. Right? What does that mean? Okay, that means if you have, for example, I think maybe we should use a reverse man of the way that's that. Okay, let's consider 2 matrices. Okay, one is P, another P prime. Okay, that means P is a P transpose. Okay, and we want to get a diagonal matrix. Okay? And let's use P's rows. Okay, for example, this is row. Okay, row. Right? This is P1, P2, P3 row. Okay, and here you transpose them, they become P1's transpose. Right? You transpose the column. Okay, P2 transpose. Okay? Now let's look at what does this mean. Right? So what's this value here? This is really P1 times P1. Right? The first row times this column. Okay, and P2 times P2. Right? So they are telling you that if you have 2 rows or columns, right, you can also show something like columns, right, by reversing them. Okay. So no matter if you just zoom into a particular row format of column format P, these 2 rows, any 2 rows, right, any 2 rows that is the same, it's the length of the vector is 1. Okay, because if you think about P1, inner product with P1 is 1. That means it's vector length. But in the meanwhile, if you time P1 with another vector, which is not the cell, right? It will be 0. This is the first row, second column, it will be 0. Okay? So that's a conclusion. So you can decompose P into different rows according to columns, okay? And the same row, the same column, the length of the vector is 1, but for any 2 different rows or different columns, okay? They are orthogonal, right? So this is what is P is orthogonal. And if that happens, we know that this is equivalent to inverse, right? Because P times P inverse is diagonal, right? So again, now we can make since we can get rid of minus, we can just use a transpose, right? Because if you use a inverse, there's an adjoint, how to say adjoint, right? So anyways, there's a very complicated computation, right? But if your P matrix is orthogonal, the inverse is very simple. Just to do a ij swapping, okay, then you get the inverse matrix. Okay, so that's a pretty, pretty straightforward, and so very easy to compute, also, right? And so here A is a solid diagonalizable, right? It's equivalent to saying that A is equal to this, right? So the reason is A is similar to D, and in the meanwhile, so this A is diagonal. Meanwhile, the P is an orthogonal matrix, right? We discussed it. Then previously, if you remember, we have this equation. We have this equation, but this transpose is minus, right? Now we can replace minus with transpose because they are equal, okay? And equivalently, you can left multiply P here on both sides, right? And the right multiply P inverse over the P transpose, okay? Then you get this. Okay, these 2 cancels on the other side. So we will actually stick to this straight, okay, this straight. A equal to P times a diagonal matrix times P transpose, where P is orthogonal, okay, and D is a diagonal matrix, right? If that happens, and you can represent things like this, A is orthogonally diagonal, okay. And another important thing, this is pretty much very similar to SVD, okay. Again, it's not intuitive initially to you guys, but as time goes by, you need to be very clear. So you need to be immediately see, hey, this thing is this thing, okay? But here we will do some derivation to show you how to do that, okay? So firstly, as we discussed, I will just use a conclusion we discussed, right? If you look at P, right, and you can write it so let's look at this side first, okay? So this is what? This is the first column, P1, right? P2, okay, and Pn, right? But that's not done yet because we have a diagonal matrix, right? So we have lambda P1, lambda 1 P1, lambda 2 P2, and lambda n P. Okay. Now we want to time P transpose, right? What is P transpose? Remember, P is a column, right? So if the transpose becomes row vector, right? But P1 is a column vector, so you need transpose, okay? All the way to Pn transpose. All right. Next, let's look at whether this is a valid, valid block matrix notation. Right? So what is the dimension of this? This is n by 1, right? This is column vector. Okay? And what is the dimension of this? Transpose is 1 by n. Okay? And this one matches this one. Then we can just do the multiplication. Okay? And again, if you look at this is like an inner product. Right? This times this. Okay? Then this is the first item times this first item, right? Which gives you the, so we are using di, not lambda. It's the same thing. It's a diagonal matrix. Right? So d1, d11, d22, because d12 is 0. Okay? And then times, this p times this p transpose. Okay? Because we can do this multiplication. But keep in mind, this thing ultimately multiplying is n by n, because it's n by 1 times 1 by n. Okay? But in order to see why we can go to this shape, we need to use this block matrix. Okay? All right, so now we are here. Let's do some deep comprehension of this formula. Right? So we talked about this is n by n, but A is also n by n. We are saying that A is a summation like of n items, okay, which are of the same shape. Each is generated by some pi. Okay? It's like A has n dimensions. Each dimension is decided by this, right? That has n components summed together, right? So this is ultimately what it means, right? And so again, A can be, usually when you do eigendecomposition, you are working on real symmetric matrix. Right? A lot of the time, it's really the so-called correlation matrix, right? Which means how variable I and variable j are related, okay? Correlated. And ji and ij, they have the same correlation. Okay? So A is a real symmetric matrix. Okay? If that happens, we can show that A is orthogonally diagonal, and we can show the reverse, which means A is orthogonally diagonal, then A is a real symmetric matrix. Okay? So actually, one side is pretty straightforward, right? So A is orthogonally diagonal means this thing, right? So you can easily show that it's symmetric. Okay, so this direction is trivial, right? This direction needs some proof for USD. Okay, so why this A of this shape, right? Why this is a symmetric matrix, right? So this is a question. Okay? So actually, you can show easily because you can take A transpose, right? This thing is transpose. Okay? And when you take transpose, you will go from this thing, then this thing, then this thing. Right? So first we look at this. This is transpose, you get back to P again. This D diagonal matrix, if transpose it, it's D again. Okay? And the P is transpose. Right? And if you look at this shape, and then look at this shape, they're the same. So it's right. And now you look at these two ultimate conclusions, right? A is transpose A. That means it's a symmetric matrix. Okay? So just to look at this shape, we will know it's a symmetric matrix. Okay? So this side is pretty simple, and this side is not so simple. Right? Any real symmetric matrix will have a decomposition like this. Right? This is not so true. There's a constructive manner to create this, but it's by eigendecomposition. Okay, finally, yeah, so we are still at the linear algebra part, right? So the eigenvalue and the eigenmatrix. Okay, we'll go to the SVD soon. Right? So again, when we talk about eigendecomposition, A is always a symmetric square matrix, n by n. Okay? And if that happens, okay, usually we think about it as a correlation matrix, right? Okay, covariance matrix. And then, the determinant A is something like this. And so the product. Okay, and there's also a concept called a trace. Okay, what is trace? Trace any matrix. Okay, you have a matrix like this, right? I think I lose my mouse. So any matrix you have, the diagonal summation is a trace. Okay, it may look pretty trivial and then nothing interesting, right? So, but trace has a lot of magic properties. Okay, so basically it captures the key information, right? Because if you think about it, trace is what? Trace is a summation of the eigenvalues, which are the features of the matrix. Okay, so this contains lots of information. Okay, and so don't. So for example, if you know Frobenius norm, right? If you take the gradient Frobenius norm of that matrix, it's a trace function. Okay, and there's a lot of relevant stuff. Right? If you took my machine learning course, okay, so here we will prove these two, right? So y the determinant is the multiplication of the eigenvalue, and the trace is a summation of the eigenvalue. Right? So let's look at the determinant first, right? So determinant, we know that a, you can write it like this, right? So you can a minus lambda I, but lambda is equal to 0, right? Then it's just a, right? But writing this has some benefit because we know that when we write the characteristic function, right? When we write this, well, this thing can be decomposed into these n roots come together, right? And some root may be complex, right? But because it's a real symmetric matrix, maybe the lambda idea. Okay, you can show it. And so if you write this thing as this thing, right, and then you still put this 0 here, you can see the conclusion, right? So you think about this is 0, then it's minus lambda, right? And there's the minus 1 cancel with you because there are only n items here and higher. Okay, it's lambda 1, lambda 2, or lambda. Okay, that's how you see this conclusion here. And in the meanwhile, we have trace. Right? Trace, sorry. This one. Trace is the same. Right? So if you write A, we know that if you say this is a, this is a symmetric real matrix, you can decompose it like this. Okay, that's the conclusion in the previous step. Right? And if that happens, trace has a so-called circular, property, which means you can move this around, and the trace will be the same value. And then you can move this around; it's the same value. Okay? So, for example, if your trace, you have ABC, right? ABC. It's going to be equal to, you move A around here, BCA. Okay, it's not going to be equal to BAC. Okay, it's just a circling in one direction. Okay, and so it's not any permutation. Right. So and here what we do is we move this around, right? Then you get D, P transfer of P, and we started, because A is a real symmetric matrix square, right? And then we can always have this, where P is what? P is orthogonal, which means transpose and minus 1 is the same. Right? I mean the inverse, okay? And they cancel, right? And finally you get trace D. So what does that mean? That means your A, if A is similar to D, right? And A satisfies this requirement, which means you can do this kind of decomposition. The square is symmetric, okay? And then what you can do is, your trace is the same as your diagonal equivalence matrix trace, right? Similar matrix trace. And we know that this diagonal matrix is lambda 1 plus lambda 2, right? And this is proved in a previous slide. Let me go here. Right, so we proved it. Okay, this is diagonal. This is diagonal. Right, so that's basically completes this conclusion. But just keep in mind that your determinant is firstly you need to remember several things. Right? So first, these eigenvalues are basically describing the feature of that A matrix. Okay, right, this is one conclusion. Secondly, if you can do the eigen decomposition, right, you can get this values. Of course, your A has to be symmetric and real, right, and a square. Okay, then you will have this property. Right, so determinant is a product of your features, okay, with the eigenvalues. Okay? And the trace is a summation of your features, okay, of the matrix. Okay, that's pretty much the review. And the next we will move on to SVD. And we will use some of those conclusions before, for sure. Okay. And so SVD is based on the concept of best fitting subspace. Okay, let's look at the brief shape of this, right? So when you use a library, let's say the linear algebra library of NumPy, okay, the first thing you need to know is what's the input, what's the output, right? And we remember SVD gives you the output, right? You put a matrix inside, any matrix value. It doesn't have to be square like in eigendecompletion, okay? And it will output 3 matrix for you, right? U and a diagonal matrix S and a V, V, right? U, V, and S, okay? Let's look at how the matrix is looking like, right? So it's kind of like magic because you can always get those 3 components, okay, for any matrix. Right? And it looks like magic, and we need to make sense of it, right? So these are the tasks of the next few slides. And the rest of the slides, it's a lot of slides, not just a few. And so originally we are talking about a data matrix. Right? We have n rows and d columns. Okay, so d is usually a feature number, right? Dimension, shorthand for dimension. N is usually a number, right? Number of rows. Okay, you just think about, for example, in pandas, right? So you have a lot of, or in machine learning, scikit-learn, you have a lot of training data, right? And each data has different variables, features, x1, x2, x3, d columns. Okay, so this is called a data matrix, n by d. Okay? We are having this kind of, pandas table in mind. You think about in data science libraries. Okay, and AI is each row, right? This is like one row of your data matrix. Right? It's a one item. Okay, and we want to show that the best fitting k-dimensional subspace for rows of A. Rows of A are the data rows that you have. So so if you look at this data space may have a lot of dimensions. Some are maybe noise. Right? Noise can introduce some new dimension, measurement errors. Okay, want to remove them, and we just want to find a smaller space that captures the major information, drops the other noise dimensions. Okay, and find the best fit k-dimensional subspace. Right? If we have a budget of k, how can we find the k-dimensions? Like these directions that captures, maps our row points, okay, into a new space. And that actually is the best fit, right? So there should be some metric saying why this is better than the others. Right? Okay. So the metrics are using so-called minimize the sum of squared distance from AI to S. Okay. So this is what we want to say. So maybe most of the data point is in this screen. Okay. So different in this screen. Okay. So in this case, we just want to say, hey, these two are your dimensions. Right? But unfortunately, you may have some noise that causing you to go out of the screen or inside the screen. Okay? But these are really should not be there. Right? These are noise. Okay? So what we want is we just recover the red ones. The anyway is the green. Okay? So this is what we are. This is the intuition. Right? And the K here is 2. You just want it's a 2-dimensional space, right? Capturing major information. Right? Okay, let's take a look at SVD overview. And again, we are not showing why SVD animatrix can be decomposed like that. Okay, we are telling you what right now. Okay, so you can write a vector X in orthogonal basis. Right? So what does orthogonal basis mean? Right? So if you have d-dimensional space, right, you can find d-dimensional vectors. All of them are orthogonal, which means 90 degrees for every vector. Okay, and their basis means not only 90 degrees for everyone, but their length is 1. These are unit vectors. Okay, these are unit vectors. If that's the case, then you can decompose them. Okay. Here, let me give you an intuition in 3-dimensional space first. Okay. Let's assume you have a. Oh, what did I do? Yeah, I choose a rubber eraser. So yeah, let's do this. Okay. You think about in this the three green arrows are 3 bases. Okay, in 3-dimensional space, and we have a x is a vector inside this 3-dimensional space. Okay, so now we want to give coordinates according to these bases. Right? How can we do that? Firstly, you will compute, for example, this is theta. If you map this point to here, right? This is cosine theta of this length. Right? So but you know that you can do it in the part because this is, let's call this vector x, right? And this call is v1. Okay. So what if you do cosine theta, right? So you want to do cosine theta times x. Okay. So this is length, but you have a cosine theta component up here, right? So this is something you want to do. But we can show that if you do this is equivalent to this, right? So this is because, what is xv1? So they are inner product. Inner product is equal to x, right, times v1. It's longer v1, right? These are times, okay? And times cosine theta. Okay? So I think this is, you should know this already, right? So if you times the inner product between the vectors, it's equal to this length, and cosine theta. Okay? And we know that this is the basis, which means this thing is the 1. Okay? This thing is 1. That's why we have this, right? And similarly, if you go, you take the inner product with v2, that is v2, then it's a coordinate on v2. Right? And you take a inner product with v3, maybe some coordinate on v3. Okay. So this is basically, you can write it like a coordinate space, right? Without the coordinates. Coordinates is the inner product with all the bases. The condition that those are bases. Right? Bases means they are orthogonal and they're unit vectors. Okay? And you span all the d-dimensional space. Right. So our goal, these two goals are equivalent. Right? So we want to minimize the squared distance, okay, from x to this d-dimensional space, right? Because maybe x has a more than d-dimensional, but the other dimension are introduced by noise, okay? And it's equivalent to maximizing the so-called squared projection. Okay? Let's take a look at the example. Right? So if you look at let's say x, right, AI, one particular row in your data table, okay? Right, so let's think about this is xi, okay? Right? And now you think about it, we have particular basis, right? So we have a particular direction basis, okay, the v, right? And we can show that, the length of the vector is always this, right? You should know 2-dimensional, 3-dimensional. This is less squared, okay? And this, this is a squared plus b squared equals c squared, right? So this, this thing squared, because this vector length is square root of this. So this is, if we are square root, this is this length squared. Okay? Should be equal to what? Should be equal to this length squared times this length squared, right? Right. So this is the constant. Okay? So these two plus together is a constant, which is determined by your data. Right. So this is what we call the distance of the point to line. This point to your line. This basis line. Okay? The first dimension. And so then you have a length of projection. Right? So this line, you have a projection. Okay? So this is your projection. Right? So this maybe, let's say, call this a squared, right? And this is called a b squared. Okay? This should be to the constant, which is the length of this area, okay? Which is c squared. Right? So because the constant, this data is given, right, in the data table. Okay? And then if you are minimizing square distance of this, right? And you are maximizing basically the other. Okay, so because their sum is constant. Right? Okay. And although you may say that this is just 2v1, right? But you have v2, v3, v4, but they are all orthogonal, which means they have no impact, right? So they are basically, if you are minimizing b1 square with b2 square with b3 square, okay, that's equivalent to maximizing, a1 square plus a2 square plus a6. They are equal to maybe 3 times the c square. Okay, so they are equivalent. Right? So whenever we say we want to minimize this kind of distance squared on all different v's, it's equivalent to say we want to maximize the projection square summation along all those we want to do. Okay? So yeah, basically. So put simply, if you want the most component to be captured by V1 right? Okay, and yeah, so this part. Then you should the orthogonal component to each dimension should be small. Right? Something like this. Okay, now let's take a look at what is SVD. Right. So let me give you intuition first, right? Before we go to the derivation. Always intuition first. Okay, if your math professor is not giving you intuition, just go into the details, right? So you will forget everything and you will feel headache. Okay. But after intuition, if you really want to get deeper understanding, maybe you can see the proof. That will help. Okay. So firstly, as we said, this is the first row, this is the second row, this is the third row. Okay. This is your data table. This is feature one, maybe age, salary, right? And something like gender, etc. Okay. And this thing actually will do a so-called dimensionality reduction, okay, from D-dimensional to R-dimensional. Okay. So now let's say this is one person or one data item. After SVD, this becomes a new dimension. Okay, that drops some noise. Okay, still one for each person. Right. So that means this is a compressed vector for this person, original table. Right. This is another compressed vector for this. Okay, we drop some noise, and it's a free vector because SVD is just library code. Okay, so this is the first way to look at this decomposition, right? And this D is diagonal. Okay, so these are the singular values. Okay, in eigen decomposition, this is square. Right? So this is called the P and P transpose. Right? So this is called the eigen decomposition. But here we are called singular decomposition. So these are not eigenvalues. These are second singular values. Okay, and those some others are called singular vectors. We'll describe these details later, but let's just look at what they mean. Okay, so another important thing to see is, this thing can go pretty high, right? At least can go to D-dimensional space, but we don't like it. We are reducing it to R-dimensional space. Right? Each dimension, how important it is, are captured by those diagonal values. Okay? These are called singular values. Okay? Maybe some are so unimportant we want to drop them. They just are because of the noise, right? Introduced by noise, right? So we can shrink. We'll see these things later. Okay. So finally, you need to keep in mind. Remember, we are talking about V1, V2, VD, right? What are they? Okay, so the intuition gives you these things bundled together is V, right? So this is intuition. So here's the V transpose. So V transpose. Remember, we want R dimensions, right? So this is V1, this is V2, this is VR. Okay, we have R dimension. We want to reduce from D-dimensional to R. Okay, this is R dimension. And then, so this is R dimension, right? So so now let's come back to this matrix. Okay, let's come back to this matrix, and let's look at previously we are looking at it like this dimension is reduced to this, right? So this is one way to look at it, but we probably have another way to look at it. Especially we are not touching too much about the interaction here, right? So actually, if we look at, for example, what are these values? So what's the first value? This first value is its coordinate along the first direction here. Okay? This second value is a coordinate along the second dimension. Okay? This third value is the third dimension. Okay? So put simply, this entire row is this. Let me see. This coordinate, but this row is one. Okay, and this V1, V2, VD are these rows. Okay. And because we usually write vectors as column vectors, so we should write this as V1 transpose. Okay? V1 transpose, V2 transpose. Yeah, I hope this will give you intuition. Okay, so this is a rank R matrix. If your A matrix has rank R, you can at most decompose into this, right? You will not have more. Okay? Even though you have D dimension, but a lot of them are redundant, right? So it's the same rule underlying generating your features, right? So in that case, maybe the rule is this is like a manifold learning, right? So it's very low rank, and in real life, right? You don't have maybe 10 rules, but you are generating 1 million different kind of observations, right? So actual dimension is only 10. It's just a different combination of them generate those complicated things. Okay, so this is called that's the foundation for dimensional reduction. Okay? And D here is a diagonal matrix, right? And by SVD, you have a guarantee that all these diagonal values are positive real values. Okay? Of course, we will list from the biggest one, which is the most important first dimension, and the second one is less important second dimension, and then more even less. Okay, so we'll listen. So these are the weights DII, okay, of the dimensions. And they are always positive, okay, because it's how important that dimension is. I see the chat. Again, we are talking about what, not where. Small real-world implementation to show how this transformation works. Yeah, we will go to a application in the next slide, but here, because we are talking about the shape, right? Let's finish the shape, and then we'll go through the real world. Right. So in most cases, the real example is in here. Original dimension, d-dimensional space is redundant. Right? We want to transform to a smaller r-dimensional space. Okay? And these are the coordinates of this point in the new coordinate system. Okay? And these are how each component is important. Right? And we will see this in the next few slides. And these things have to be memorized, unfortunately. Okay? Otherwise, you cannot even call those libraries to use them. Right? And so another important concept here is U and V, right? These are so-called orthonormal columns. Okay? So which means, if you remember, we have a P, right, which is the orthogonal matrix, right? But this has to be a square matrix. Okay? Then every row, each two rows are also, okay? Each two columns are also. But we don't always have this, right? So here we are not considering square matrix. So this U will be n by R, R by R, R by D, right? You know, right? So U will be something like this, okay? And the V will be something like this. They are not square. And in those cases, look at, for example, we are looking at V1, V2, VR, right? Something like this. Okay? Of course, this is V1, V2, VR transpose, because whenever we list the vector, we are talking about row vector. This is column vector. Okay? This is row vector. These are also, okay? Which means the length of this vector is 1. Okay? And any two vectors are also. Okay? This is the reason we have the basis, right? So, and so the other thing is that says U1 to UR, right? So here we are not looking at rows like in here, right? So we are looking at columns. Okay? U1, U2, and UR. Okay? We can show that these different things, okay? These different things are also often these different, okay? And they are because also normal. So each of those columns, okay, has length 1. Okay? And if you have any two of them, they're also. So these are the conclusion. So this is how we look at here. Okay. But actually, when you use it, you look at the row. But when we derive SVD, we think about it. Okay. So they're orthogonal because these are independent dimensions, right? Corresponding different new dimensions. Okay. So and yeah, so this is this is just describing that if you delta, I and j is the same, they're 1. Right? And I, j is different, that's it. Okay. This is just saying they are orthogonal. Okay. But that's only one side, either row or column. Right? So this is also not normal column. And if you transpose it, okay, so these are just the orthonormal columns. Rows have no guarantee. Okay. Next is something we see before, very similar, right? So we can show that if you can write something like this, okay, it's equivalent to something like this, right? Okay. How can we see that? Right. So again, remember, if we do a diagonal matrix on the right, it's like times this U1, right? So this is original U1, now it's maybe D11 U1, okay, D11 U1, okay, and then this is D11 U2, okay. This is row, which is the output of this. And now you write this, right? So if you look at here, you have to transpose. We told you that this is U1 transpose, okay? And VR transpose, okay? Now let's come back, okay? So this is, these two dimensions actually match, right? So because this is, this is a column, and so R, right? And this is row, right? So they start from R, okay? Right? So they actually match, okay? Then we can do a dot. It's like an inner product. Okay, so with this. Okay, so D11, U1, V1 transport. Okay, U11, U1, V1. Then we will do in the product, which is summation until the last one, which is R. So we have R. Okay, I from 1 to R. Okay. Any questions? Again, so you can regard it like this. So if you look at these two, so UI is what? UI is n by 1. Okay, n by 1. Right. And what is V? Right. So this is 1 by D. So this is one. This thing is n by D matrix. Okay. We again have R n by D matrix. There are to generate this n by D. Okay. So this is very equivalent, very similar to the eigendecomposition, right? But again, eigendecomposition on the square matrix. SVD can be done on n matrix. And R is a rank of it. So there are so many dimensions only, right? So you don't go beyond that. There's no more component. But in reality, when we use it, we will drop those low DIs, okay? Listed a little later here, because these could be the noise, okay? That's similar to PCA. PCA actually is an application of SVD. Okay, so next, let me see how many pages we have. Right, so just in case you, yeah, let's up to here, then we take another break. Okay. Yeah, these things you need to memorize. Okay, so the shape and these is what's the meaning there. Okay. If you forget, you need to watch the video again and then keep them in mind, okay? Because that's, it's calling the library itself is useless. And you need to know what you are doing. Then, then you can use it in your data science projects. Okay. All right, so let's compare eigendecomposition with SVD. Right, eigendecomposition A should be a real symmetric matrix. Okay, usually it's a covariance matrix. Okay, and which means you already have those n data. Right, but you see how different data items there are different attributes x1 correlated. Okay, and then once it becomes a real asymmetric matrix, then you can it's a square. Right, then you square symmetric has to be squared. Okay. Then you can do the eigendecomposition, something like this we discussed earlier. Right? Well, D is a diagonal, and VT is a third dimension. Okay. And here the lambdas can be negative. Okay. But if you are doing so-called covariance matrix, it cannot be negative. Okay, that's the foundation of PCA, right? Because it's not just a symmetric matrix; it's called a positive semi-definite. We will see that later. Okay, it's a positive symmetric matrix. And so next, let's look at SVD. Right? SVD is defined for all matrices. Right? So you don't have to be a square matrix. Right? You don't have to be symmetric. Okay? You don't even have to be square. Right? Any matrix you can call on SVD. Right? And that's kind of like magic, right? And not just square. And we can show something like this. Right? It's very similar to eigendecomposition. Okay? Right? So remember, previously we say eigendecomposition is something A times Vi equal to what? Lambda Vi, right? Now they are telling you, hey, since the Vi dimension after transformation, linear transformation, you get Ui. Ui are those U matrices on the first one, then this. When you do A on this, you will get this. So this is what this. And similarly, if you do the transpose A, then you will get the reverse operation. The transpose on UI, UI will get UI. Okay? So this to memorize this, you just think about it equivalent to kind of similar to eigendecomposition. So, but it's not the same space. One is in U, one. And in eigendecomposition, just P, right? Previously with P, they are the same space, they are the same matrix. Here we have different matrices. And the DII must be positive, unlike here. Okay? DII must be positive, right? Because this is how important this VI is. Okay? But again, we will show why these are like this. Right now, we are giving you a conclusion to help you memorize these things, and then you will see these things unfold. Okay, but eigendecomposition, although these eigenvalues can be negative, in reality, we never do that. Okay? We usually use a covariance matrix so that these things will be positive. And now, another interesting observation is this. Right? So what if I time this A transpose on this thing? If we time A transpose. Okay? What if, again, this will be shown, right? So these two conclusions will strictly prove them. Okay, so no worry, just take for granted for now, okay, because we are getting you over. And so if we do this, right, these two is this thing, and then we have this, but this di is scalar, we can move to the front. And this gives you A transpose, this gives this thing, right? So and this thing, so di is at the front, okay? And this thing is this thing. So this is di squared di. Okay? So the conclusion is that if you do this, right? So as I said, this is basically equivalent to this one, but this one is the real symmetric matrix. Right? If you look at this and you take a transpose, it's itself. Okay? This is null. So they are equivalent in some sense that SVD is saving your effort to do the data matrix transpose something. Okay? If you are doing PCA, it's just doing this and then do the eigenvalue. They are equivalent. Okay? If you are doing this, right? You will get exactly the same dimensional reduction effect. Okay? It's the same VR, right? Same vectors, right? The new space. Okay? But your eigenvalues will be squared. Okay? So the single value is DI, right? So the eigenvalue is DI squared. Okay? So there's this kind of relationship. Okay? But again, this VI is the eigenvector of A transpose. This is the conclusion. So this is called a covariance matrix. We will see later. Of course, you need to divide by n if you have any rows. Okay. But basically, this is a constant factor. So it doesn't matter. Okay. I know it's a lot confusing, so we will show you why, like something like this. But so this will show this in the next few slides. But I think we'll take attendance and we'll take a break. And then okay. And there are a lot of interesting things like in linear algebra. Okay, so it's kind of like magic, right? So you assemble a bunch of numbers into a square shape, right? And then you have so many magic stuff there, like eigen decomposition, and you have those kind of like a spectrum stuff, and you have trees, like those kind of things. Okay, so if you have interest, actually at UB, there's a professor in the math department, gave a very good tutorial. I mean the materials, right? You can review these things, but maybe for this course it's not really necessary. Okay. And there's also a matrix computations. This is more on computing side. Right? It's not that hey, I'm comfortable with this. That's right. You need to compute these stuff. So how to compute? I know I can decompose this, but how do you get this p? How do you get this lambda? That's CS people you need to care about. Okay? And how can you compute them efficiently and in reasonable time? I know it's there, but how to compute it? Okay, so let's take attendance and then we will continue. We will take a break and then we continue. Due to the time, we will just sample some students. Okay. Let me see. I'm losing track of my mouse. Just a moment. Okay. Yeah, it's fine. Okay, Joshua, are you here?
Yes, I'm here.
Okay, thank you. I lose my mouse again. Deepsy, are you here?
Professor.
Okay, I probably hear you. Right, Deepsy, you are here. I can confirm. Hello, Deepsy?
Yes, Professor, I'm here.
Oh, okay, so your name is Deepsy or Deepti? Just want to.
Professor, I'm here.
Yeah. So your name is Deepti or Deepsy? Just want to pronounce correctly. Okay.
I'm Deepti and Chepasavini.
Yeah, it's okay. Yeah.
I'm Deep.
Okay, yeah. All right, so let's go to Hasha. Hasha, are you here? Hasha? Hasha? No? Let me know if you are here. Okay, I can correct them. Vashini, are you here?
Yes, Professor, I'm here.
Okay, thank you. And Chun Yao Chen, are you here? Chun Yao Chen?
Hello.
Oh, yeah, I saw you. Okay. Yeah. Xuping Chen, are you here?
Yes, Professor, I'm here.
Okay. Thank you. Vivek, are you here?
Yes, Professor, I'm here.
Okay, thank you. Daniel, are you here?
I'm here.
Thank you. Bahanutija, are you here? Bahanutija, if I pronounce correctly? No? Sun Kang, are you here?
Yeah, I'm here.
Sunjo Lee, are you here?
Yes, Professor, I'm here.
Thank you. Gaushik, are you here?
Yes, Professor, I'm here.
Cole, are you here?
Yes, I'm here.
Okay, thank you. Sunnykill, are you here?
Yes, sir. Sir, I'm present, sir.
Okay, thank you. Harish, are you here?
Yes, sir, I'm here.
Thank you. Khadija, are you here? Khadija? No? Tom, are you here?
Yes.
Okay. Shangsi, are you here?
Yes, Professor, I'm here.
Okay, thank you.
Khadija
Carmen.
responded.
Carmen, are you here? Oh, I see the chat. Yeah. Carmen?
I'm here.
Okay. I will correct the others from the chat after this. Okay.
Hey, Diane, just got disconnected. I got back now.
Yeah, I will correct it. I saw you. Yeah. Boniface, are you here? Boniface?
My name is Banteja.
Here.
Yeah, so Boniface Singdala, are you here? I will correct
here.
Okay, got it. Sushimisa, are you here?
Yeah.
Okay. Sushimisa?
Yes, Professor, I'm here.
Okay.
Yes, Professor, I'm here.
Chantan, are you here?
I'm here.
Got it.
Yeah,
Let me correct here.
So Banuteja, yeah.
Yeah, I will correct them. Okay, but you need to continue and then come back. Hasha, are you here?
I'm here, sir. I'm here.
Hasha?
Hello, sir. I'm here.
You are here, but I do not see your name, right? So I see the Amulya's name, right?
Yes, sir. Like my phone, I lost my internet connection. Sorry, sir.
Oh, I see. You are with. Okay, it's okay.
ఏమంట గ్రూప్ లో ఏమో మెసేజ్ పెడుతున్నారు చూడు
Here?
Can you hear me? I am here.
Okay. Yeah, let's take a 10-minute break. Okay, we'll come back maybe. I think it's almost 7. Right? So we'll come back at 7:10. Okay, right. We'll begin right at 7:10. Okay. Some student I haven't called the name because I sampled, right? So I don't call all the name. Every 3 I call 1. Okay, next time I will shift a little bit and call again. Okay, we want to save time. So we will sample 1/3. Yeah. Okay. Let's take a break and we will come back and start SVD for maybe 10 minutes. Okay, let's continue. So, before this page, okay, before this page, everything you don't need to understand how things are derived. Okay, it's like let you memorize and get some intuition of those things. Okay, but starting from this starting from here, everything, if you don't understand, you need to see the proof and ask yourself and look at the slides, because everything is rigidly proved one by one. Okay, it doesn't mean that the previous, the slides we quickly go through earlier are not rigidly proved. Okay, it's rigidly proved, but we don't have time to prove these, right? It can spend half a semester to prove those things in linear algebra course. Okay, we just let you accept it, right? Because you might not have basically we give you a refresh, right? You might not have a strong memory of those stuff. Okay, but from now on, everything is strictly proved. Okay. So firstly, what we will do is we will, if you remember, SVD, we have these things, right? So we will go through things like this. We will first show that these vectors are best fitting directions. Okay, we first find those vectors, how to find those vectors. Okay, and after that, we'll show that how important each one is are those, singular values. Right? Finally, we show a constructed proof that U's what are they? What are they? Okay, so construct proof is actually using this conclusion. Okay? Just to give you guys some intuition why we are proving these. Okay, we'll use this. Right, so U is this thing divided by DI. Okay, and then we'll show, hey, this inputting back it's really A. Okay. Yeah. Okay, now let's first think about those V, right? Those directions, those dimensions that we want to map to. Okay, so we call it the best fitting line because so we want to, for example, if you have a bunch of points, right, you think about point, okay. Apparently, if you go this line, it captures most of the information. Okay, right. Let me see here the chat question. Right. So on the other hand, if you go the other direction, right, like this line, this is a bad direction because when you map those points to this line, it's almost the same position. You cannot differentiate, right? Okay. So that's the intuition. Right? So these points are not too far away from this line, but if you look at this line, a lot of points are very far away. So this is a bad direction. This is a good direction. Okay. So we want to find a best fit one-dimensional line, like this green, the blue one, okay, not the green. Okay. So this is intuition. So we are finding V1 okay, first, because we know this. We have a basis V1, V2, V1. Okay, and they should be orthogonal, which means V2 should no longer consider any information already contained by V. Okay, let's continue. So we first think about how to find the best fit one-dimensional line, V1. Okay, and then we repeat this, for so many rank times. Okay, right. So each time we will find the next best fitting line that is orthogonal to all the previous ones. Okay, so this is what we are doing. So let's assume that V is a unit vector along the best fitting line. So we want to find this basis. So first V. Okay, and we know that if you have a row of your data table AI, right? The length of the projections is right. We already told you this is inner product. Okay, this is the coordinate along this line. And now, so what is the sum of squared projections, right? So this is our question. So if you look at the previous, I think we have a slide on that. Just let me find it. Yeah, this slide. Okay. So we are saying, hey, if you have a particular data point, this data point, right? If you use vector form, it's this, right? And your projection along V is this. Okay. This is maybe the first row in the table. Maybe you have a second row in the table, like something like this. Maybe you are at this point, which means you have this, and then your projection is this, right? And we wanna compute this, right? So keep in mind, we wanna minimize squared distances, right? We wanna, let's say this is 10, this is 2, right? So there's a sum of distance 2 square times 10 square. Okay. And for each row, we have some projection along this thing. Okay, we have some value square. We want to minimize this summation. Okay, so this is what we are doing here. And let me see here. Yeah. So we can represent this stuff using this. Okay. So what does this mean? Right. So why sum of square projection lengths is this? Right. So again, you need to write it out like A is what? A is the first row, the second row, and the nth row. Okay. Then you will see. Okay. So what is A times B? Right. So and A times B is, this is one row, right? This is one column. So this block matrix can work. So you can write it as AV, A2V, and AN. Okay. So something. So this basically explains what is AV here. Okay. Right. But we have, this is basically a column vector. Right. So this is inner product, row times a column, one value. So this whole thing is a column vector. Okay. So the column vector, this is a L2 norm, which is a square, right? So this is the L2 norm, which is this value square plus this value square plus this value square summation, right? And then k square root. Okay. And if you compute the L2 norm square, you take out the summation. This gives you something like this, right? So A1, V1, okay, square, right? Plus A2, V2 square, plus AN. Okay. Something like this. And this exactly is a sum of squared projection. As we explained, each one is a projection along. Right? This is A's projection along. This is A2's projection along. Right? So this is inner product. Because V is a unit vector, right? We have cosine theta. If you still remember, we discussed it. Right? So this, so one thing very important is to be comfortable with this thing. Okay, because this thing is really sum of squared projections, and we want to maximize it. Right? So we want the orthogonal product to be minimum, almost most information occur. Okay, so that's the target we want. Maximize this. Find V, because A is fixed, right? So you have the databases. You want to find different V, given different unit vector, you have a different value of this. Right? You want to find that particular V, so that this value is maximized. Okay, so that's the task. So that one is the best fit. Right, so here, if you look at the first singular vector, right? Again, so in eigendecomposition, we call eigenvector. In singular decomposition, right? We put singular vector. Okay, SVD, we call singular vector. Singular vector, value decomposition. Okay. So here, what kind of V1 we have to find? This is what kind of V1 we have. If we put that particular vector here, right? This will make this value maximum. So we put argmax. Right? So argmax means if you put this V1 here, right, you maximize this. And but you don't want a max value, you want a V1. That V that maximizes the physical arg. Okay? And again, we do have some requirements. Right? So you have to be a unit vector. Okay? Because if you don't require it's a unit vector, firstly, it's not a basis. Secondly, it doesn't make sense, right? Because this, if your vector is larger, of course this value will be twice larger, 3 times larger than 3 times. Okay, so we want it to be on the same vector strength, right? Same vector length, but we want to find the direction that maximizes. Okay, and so again, so if you look at right, so max is this square or not square, it's the same. Right? So if you maximize this value, it also maximizes this value square. Okay, so we can just simplify things like this. And the ties can be, break arbitrary. That's where things get interesting, right? So you have the same singular value, okay? But that singular value is exactly equally important to dimension, right? And then you can first pick this as V1, and then next V2, right? Okay. So this is kind of also similar to the eigendecomposition. You have the same eigenvalue, right? You have a subspace of eigenvectors. It's kind of similar. All these eigenvectors are equally important. Here you got singular vector. Okay. Now let's remember we have the singular value, right? So if you put this such a V that can maximize this value here, right? and then you put it back here. The maximum value itself is called a sigma 1. And this is the first singular value. Okay? We will show that it's really in the diagonal matrix, this is the first value. This is how important. So how much information captured. So I think something which you control. Okay. Remember, this is a sum of squared, projection x, right? Then you take a square root, you get this signal. This is the first thing. Okay. See, they are all, physical. But keep in mind, we are just defining V1. What is V1? This is strictly defined. This thing is just a definition, and later we'll show this is really the first value in the diagonal matrix. Okay, but right now it's just a definition. Okay, we call it first singular value. Okay, later we'll show this thing should go to the first entry in the diagonal matrix. Okay, and again, so here, let me see. Here, sigma 1 square is this thing square, like this thing square, and you can show that this is what we just described for you. Right? This is each one and the lines. This direction, you have a projection and the square and something. Okay? But this thing is square root of this. Okay? Only this sigma 1, the first singular value square is is this thing. Okay? Is this AB, modulo square, okay? L2 norm square. Right, so this find the best fit one-dimensional line, right? Now we want to repeat it, find the next line, right? The next best line captures most of the remaining information, okay? And we can do this until projecting zeros, and there are no more component that you can take by any direction. That will stop. So the next one is quite similar to the first one. The only difference is we need to be orthogonal. Okay? Otherwise, it's the same. And the second single value, okay, define single. Okay? And then we can, maybe we still have some component along some directions that we not capture. Right? The case requirement is orthogonal to all the previous k minus ones. Okay? And then you find the best. This is kind of like a greedy, right? A greedy solution if you look at it. Right? But we show that the greedy is also optimal. Right? Okay, so that's a lot of greedy algorithms are locally optimal, but globally you can make a better result. But SVD will tell you that this greedily choosing the V, right? First choose the most important V, and second most important V, and third most important V. Right? While you are guaranteed they are unit vectors, and also the previous chosen basis. Right? This actually is the best fitting. Okay? We will prove that. And yeah, we will show this. Although greedy, this is actually the best subspace according to data A. Yeah, let's prove this. Okay, so first consider k equal to 2. This is induction. Okay, so first think of the base case where k equal to 2, and then let's assume that we have a best fit two-dimensional subspace. Okay, so k is this k, right? So we already V1 is pretty clear, right? So because V1 is always the best, okay? But V2 has some restriction, right? So orthogonal, but we want to show that we have this orthogonal requirement, okay? It's still the best, right? So we consider a two-dimensional subspace created by any two, vectors, okay? Let's say any orthogonal basis. It may not be V1, V2, right? It could be W1, W2, any two orthogonal basis inside this two-dimensional space, generated by V1 and V2. Okay? So what I mean is, for example, originally maybe it's this space, okay? Say we generate whole screen. But maybe you want to find you want to show this is best, right? You want to show, hey, if I give two other bases, right? Okay, orthogonal bases. So you are not better than this green. Okay, so this is the idea. So for any orthogonal basis, W1, W2, right? In this two-dimensional best fitting subspace generated by V1 and V2, right? We want to show that the sum of squared projections, which are those. And so they are not better, not more than AW1 and AW2. So we are showing something here. Okay? We want to show this. And then V1, V2 is the very best because this is arbitrary, right? No better than this. Okay. So how to show this? Right. So we can choose a W2, right, to be orthogonal to V1. Okay. So how can we achieve that? Right? So So case one is, what if the W2, W1 is not V1 for them? Okay? W2, then we want to choose a orthogonal basis for W2, right? That is orthogonal to W1, but not be maybe orthogonal to V1, right? Because W1, V1 are different. Okay. So if it's already orthogonal, but we can get a W2 that also orthogonal to V1. Okay? How can we do that? Right? When we work on the second dimension, right? W2 is W2. Right? Okay. When we choose W2, if the best fitting space generate V1, V2, right, is orthogonal to V1, right? So then any vector works, right? Because your W2 is in this space, okay? W2 is in this space. So what if your W2 is not orthogonal, right? Orthogonal to if this doesn't hold, right? So this W2, the choosing space is not orthogonal, right? In that case, let me see. Then you can decompose V1 into two components, okay? Right, so one component is, remember we are talking about a space now, we are looking at W1, W2. Okay? We are mapping V1 onto this space, okay? Right. And let me see. Let me see how long the proof is. Yeah, this proof is a little bit long. Maybe we will continue next time, okay? Let me see. Okay, so that's all for today, I think. Starting from next time, we will see a bunch of proofs that shows you that SVD is correct and it's really of that shape, and there's some properties. Okay. And that so what I would like to recommend you guys is to familiarize with what we just taught today. Okay, so because these are the basics, right? So next time we will use a lot of the properties in linear algebra. Right? We spend 2 hours just to recap what is taught in linear algebra. So I would like you guys to familiarize with this stuff by looking at the slide, if necessary, look at it. Okay, and then next class it will be smoother. Okay, when we talk about all those proofs. Any questions? If not, I probably will end because we cannot finish the proof in maybe 3 minutes, which is the end of the class. Okay, if you have no question, I think I will end this class. Okay, I will be staying here for maybe 1 or 2 minutes, and if you have any questions, feel free to ask me. Thank you.
Thank you, Professor.
You're welcome.
Thank you. Have a good one.
You're welcome. Yeah, if you have any questions, feel free to ask me now.
Thank you.
You're welcome. Okay, it seems that there's no more question. Then I will just end. And if you have any question, feel free to send an email. And you can also go to the TA office hours. It will help you guys out. Okay. Thank you.